we're going to learn about the geocentric universe. So way back, the 2,000-3,000 years ago, the ancient Greeks came up with some ideas about what the structure of the universe is. And when we say universe, we really mean the solar system. And we're not going to get into it here, but one of the reasons that their universe looked the way it did was because they could not see evidence for the Earth moving. So what they did was to say, okay, the Earth is in the middle, and all of the planets and the sun and the moon, they all orbit the Earth. So here you can see a model of it. We've got the Earth in the middle with the moon going around the Earth. And then here's Venus, Mercury will be in between, the sun, Mars, and also Jupiter and Saturn, because we can see those without a telescope. They would all be inside this giant sphere where the sphere is covered in stars, and that is the entire universe. So let's look at this in a little bit more detail. So here I've got this geocentric universe, the Earth in the center, the moon, the sun, and in fact, all of the planets that can be seen without a telescope, all moving in a direction that is counterclockwise. All of these objects are in circular orbits. They're moving in perfect circles around the Earth. The Earth is just stationary in the middle. All of these objects, the sun, the moon, Mars, Jupiter, they're all perfect spheres. And they're all moving at constant speeds. So the moon is moving at the same speed all the time. The sun is moving at the same speed all the time. See here, I've got the stars on the background. While all of the planets are moving in this counterclockwise direction, the stars on the inside of this big sphere are moving in the opposite direction. Okay, but there are some problems with that model. And one of them is what we call retrograde motion. Basically, what we have here is an image of, this is what Mars looks like relative to the background stars over the course of 6, 7, 8 months. So every week or so, there's an image of Mars taken, and we can see that it's moved relative to the background stars. Normally, it's going to move eastwards across the sky. So it's going to move in this direction. But what happens is that every so often, it's going to change direction and go back in the other direction. But then changes direction again and goes forward. So when it's going in its regular direction, we call that prograde. When it moves in the opposite direction, it's moving backwards, so we call it retrograde. So this idea of retrograde motion is just the occasions when planets appear to go backwards in their orbits. And this is tricky to explain in the geocentric universe, with the Earth not moving and the planets moving in perfect circles. Let's take a little bit more of a look at what this looks like on the sky. So here we can see a nice star field, and what we're going to see is Mars moving across the sky. So here's Mars, about a week later, another week later, and each time it's observed, it appears to have moved a little bit further east. And it keeps moving east, but it seems to be slowing down, and now it's going in the opposite direction. This is retrograde motion. It appears to be going in the wrong direction relative to the background stars, but now it's turning around again. And now it's going prograde. It's going back in that easterly direction the way we want it to. And so this is what we call retrograde motion. In a second, you'll get to see the dates for when all of these observations were taken. So here you can see this one was April all the way through to October. And this is with Mars moving through the constellations of Sagittarius and Capricorn. Let's take a look at another one. This time we're going to have both Mars and Saturn. So here's Saturn, and we're going to watch as, every week or so, it's going to move a little bit, and it's moving in an easterly direction like we expected. We can now see coming in at the top here, we've got Mars moving in, and every week it's moved a little bit further to the east. But now look, Saturn is slowing down, and it's started to go back in the wrong direction. Now Mars is doing it. Mars has slowed down, and it's going back in the opposite direction. And it's going to keep moving in the opposite direction for a few months, and then it's going to slow down again and turn around and keep going. So we've got prograde motion, retrograde motion, back to prograde motion. Here we can see Saturn went retrograde for a while, but now it's turned back around, and now it's going. And now we can see the dates of the observations. You can see it's about every week or so, and at this time you've got Mars and Saturn in the constellations of Libra, Scorpio, and Ophiuchus. So one of the problems that we have is that in this old ancient Greek idea that the Earth is in the middle and the planets are going around in perfect circles, it's very hard to explain why planets are going backwards. This is the idea that Ptolemy came up with. So this is called the Ptolemaic model because Ptolemy came up with this idea. So you've got a planet that is orbiting the Earth on a perfect circle, but it's on another perfect circle, and that one is going around at the same time as the whole thing is going around. So I'll show an animation so this is a little bit clearer. What we've got is as the planet goes around this way, this circle is going to go around. So every so often it's going to appear to go backwards. So let's take a look at that. So now here what I've got is, here's the sun going around the Earth, and here's Mars, and this is its main orbit, which is a circle, and then it's got this other smaller circle that it's going around on. The main orbit is called the deferent, and the smaller orbit is called the epicycle. But you can see how it's going in the right direction. It's going the way it's supposed to be, easterly across the sky. It's quite happily going along, but now it seems to be slowing down relative to Earth, and it's moving in the wrong direction just for a little while, and then it starts going back in the right direction again. So this was the solution that Ptolemy came up with. And so now what you can see is how this fits together for the whole of the solar system. You've got the Earth in the middle, you've got the moon going around the Earth, and it's got a little epicycle. So deferent is the big circle, epicycle is the little one. For Mercury and Venus, they can't get that far from the sun because in reality, they're never going to be on the opposite side of the Earth to the sun because they're between us and the sun. So their epicycles are tied to the direction to the sun. Once we get out to Mars, Jupiter, and Saturn, you've got the big orbit, the deferent, and the little orbit, the epicycle. And then here we've got the stars on the outside. And so this seems to be a satisfactory way to explain why the planets seem to go in the wrong direction briefly every so often. But there's a problem, and that's that although this model does answer the question as to why the planets seem to go backwards, it's not very satisfactory. One of the problems is, so here I've got the Earth and Mars on its deferent and its epicycle, is that over the course of a couple of decades, you'd have to fix both the size of the deferent and the epicycle and how fast the whole thing is moving in order to match the observations. So we can see where Mars is, and if you can't make it so that it works forever, then that's not a really great model. And that means that you can't use it for predicting where the planet's going to be in the future. And so the model isn't really good science. But the other problem is that there's no unifying rules. That is to say that there's nothing that says, you know, the inner planets must be they must be moving faster or slower. There's no rules about whether Mars's epicycle is moving really fast, and as you go further out, it gets the planets get slower, and so that's just unsatisfactory. You'd like to have some rules that say, you know, the planets, here's the rule that says how this planet's orbit should be working. So let's take a look at what happens in reality. Why do we really get retrograde motion? So here I've got the sun, the Earth's orbit around the sun, Mars's orbit around the sun, and from where we are on Earth in this position and Mars here, we're going to see it relative to this constellation. This is Leo. It's looking like it's in this direction. But what happens as time goes by is that it appears to be moving in that easterly direction, but as we catch up with it and overtake it, it starts to look like Mars is moving in the wrong direction. It's moving back towards the front of the lion instead of moving towards the east. But as we get past it, now it appears to be moving eastward again. So we can understand how retrograde motion works in terms of us overtaking the planet that is moving slower than us because it's further away. So this is showing a static image version of that. Here's the sun, here's the Earth's orbit. This could be Mars or Saturn or Jupiter. And when we're in position A, this is where that outer planet is. So from the point of view of where it looks like on the sky, it's going to look like it's here. But as we progress to B, well, now it seems like it's moved in the right direction. It's moving east. Now as we get to C, we're looking at that where the planet is, now it's moved backwards. We move around to D, now we're looking at it and we're definitely looking backwards towards it. And by the time we get to E, now the planet seems to be moving back in the direction it should be moving. So we can understand retrograde motion in terms of the Earth overtaking the outer planets. And this image just gives you another view of that, where here I've got the sun in the middle, here's the Earth, here's positions that it is in its orbit, and where Mars is in its orbit at the same time. And so you can see how over the course of its of being overtaken, Mars is going to appear to do this little loop where it appears to go backwards for a little while. And that brings me to Occam's razor. Occam's razor basically says that if you have two equally good models, that is to say that your two models match the data equally well, then the simpler one is probably correct. Now, the problem is that when Ptolemy came up with this, there wasn't another model, and there wasn't going to be another model for centuries. But later, we'll find out how Occam's razor applies to understanding that the heliocentric model, putting the sun in the center and having the Earth moving, gives us a much better model for understanding retrograde motion.